Hello everyone. So this is the study guide for Physics 112 final. So let me read the first problem for you. A positive charge of 2 nanocoulomb is located at 3, 0, that's a coordinate, and a negative charge of 2 nanocoulomb is located at 19, 0. Find the magnitude and direction of the resultant electric field at 11, 6. The coordinates units are in meters. So these 3, 0, 11, 6, etc. are given in meters. All right? So we want to find the net electric field. So this is how you set up the problem. The first charge, I call it QA, is 2 nanocoulomb located at 3, 0. See, this is a coordinate x-axis. And at 19, 0, charge QB has negative 2 nanocoulombs. And you want to find the electric field at 11, 6. So this is 11, and then up here the y coordinate is 6. Okay, so 3, then I count 1, 2, 3, 4 up to 11, and then go up 6. So that's 11, 6. All right. So of course I make it symmetrical, and so first of all, you have to know that positive charge electric field will be directed away from the charge in this direction. And for negative charge, it will be directed towards the charge. So since this is 2 nanocoulomb, this is 2 nanocoulombs, the distances are the same. You can check it. This is 8, this is 8. So this distance you can find out. I'm going to tell you in a second. And from here to here is 6. So then the y component of these electric field will be E, the one coming from EA will be upwards, the one coming from EB will be downwards. They will cancel out. So the one in the x direction, they will add up, and this will be your net electric field. So now you already know the answer for the direction. The direction will be towards the right. Now you need to find the magnitude. So in order to find the magnitude, first of all, you want to find electric field E coming from charge A. So let's find that. EA is equal to KQ by R square, and K is, as usual, 9 times 10 to the power 9 Newton meter square per coulomb squared. QA is 2 times 10 to the power minus 9 coulomb, because that's nanocoulomb. And then R square is 10 meters square. How do I get that 10? Because this distance is 10. How do we get that? This is 8, this is 6. So R is square root of 8 square plus 6 square, which is 10 meters. Okay, so 10 meters squared. I work it out. I get EAX is equal to EA is equal to 9 by 15 newtons per coulomb. Now I need to find the x component, because y component will cancel out. I need to find x component. X component is obviously EA cosine theta. So cosine, so I need to find this angle from this triangle. This height is 6 and this distance is 8. So tangent theta is equal to 6 by 8. Tangent theta is opposite by adjacent. 6 by 8 is 3 by 4. I find the angle to be 36.87. So I use EAX is EA cosine theta, which is 9 by 50 times cosine 36.87 degrees, which I found to be 0.144. Now, in order to find EX from B, it'll be the same value, because two charges have the same magnitude. So now they will just add up. So that means I just simply multiply the EAX by 2, which gives me 0.288 newtons per coulomb. So in the test, some people might get this is negative, this is positive, or some people might get both positive charges, or some might get both negative. The coordinates will be different, but the idea will be the same, exactly the same, right? Okay. Now, we go to the next one. The next problem is a positive charge. Number 2 is a positive charge of 4 nanocoulomb is located at 2, 0, and a negative charge of 2 nanocoulomb is located at 8, 0. Find where the electric potential will be 0 on the x-axis. So the coordinate units are in meters again. So in order to do that, first of all, we set up the problem. And on the coordinate axis, 4 nanocoulombs at 2, 0, and this is positive charge. The negative charge is at 8, 0, negative 2 nanocoulomb. Obviously, this is positive charge, this is negative charge, right? And potential just add up as a scalar function. You don't need the direction. So somewhere in between, there'll be a point where there is 0 potential, somewhere in between. So let's call that point A. And since I do not know where it is, I'll call that it is distance x away from the negative charge. So obviously it'll be 6 minus x meters away from the positive charge. Why is that? The whole thing is this is 2, 0, so x value is 2 here, x value is 8 here. So the distance from this point to this point is 6. That is 8 minus 2, that is 6. So the total distance between the two charges is 6. I call this distance x, so this is 6 minus x. All right? And the formula for potential is simple, kq by r. So kq1 by r1 plus kq2 by r2 is equal to 0. And k is just a constant. They will cancel out in this equation. Q1 is 4 times 10 to the power minus 9 coulombs, or 4 nanocoulombs. The distance from here to here is 6 minus x meters. And distance from here to here is just x. And the charge is negative 2 nanocoulombs. So from here, k cancel out, 10 to the power negative 9, 10 to the power negative 9 cancel out. And so I have 4 divided by 6 minus x, 2 divided by x. So it's simple 1 unknown 1 equation. So I work it out. So 4 times x and 2 times 6 minus x, cross multiply. Then I get x is equal to 2 meters. So this should take about 5 seconds. And then A is 2 meters away from negative 2 nanocoulombs. So this point A is 2 meters away. All right? And or it will be 4 meters away from the positive charge. And that's the answer you look for. Now, the next problem, number 3, is our old friend the circuit. And simple one, find the current I1 in resistor R1 in the following circuit. R1, R2, R3 are given 2, 4, and 2. And this the battery voltage source is 12 volts. So all you have to do is find the current in R1. Now, in order to do that, I have to know that these two guys are in parallel. That means I have to use 1 by R23 is equal to 1 by R2 plus 1 by R3, which is equal to 1 by 4 plus 1 by 2. So R23 is equal to 4 by 3 ohms. So it's that simple. And then R23, this net resistance and this one, they are in series. So I just add them up. R1, 2, 3 is equal to R1 plus R2, 3, which gives you 10 by 3 ohms. Okay? So now we use V is equal to IR, and V is this V, I is the current going in the whole circuit, and R is this net resistance, so that I can use V and I can find I. Notice that at I is the same I that will go through R1. Only when it goes to this branch, it will go to R2 and R3, so it will branch out. So you will have two different currents. But in R1, that will be the same as this V is equal to the one you get from V is equal to IR. So I is equal to V by R, 12 volt divided by R is 10 by 3 ohms. So the answer is 3.6 amperes. So I1 is the same as I is 3.6 amperes. Okay, so that's number 3. Very simple. And now number 4. Number 4 is a positive charged particle of 3 nanocoulomb, has velocity 10 meters per second and directed into the page. The particle is in a magnetic field of 2 Tesla, which is directed to the right. Find the magnitude and direction of the magnetic force on the particle. Okay, so it's a very simple problem because there's only one formula you have to know, and that is F is equal to QVB sine theta. Q is the charge, V is the velocity, B is the magnetic field, and theta is the angle between velocity and the magnetic field. In our case, it is perpendicular, so it's 90 degrees. So V is going into the page. As we said, velocity is going into the page, and magnetic field is directed to the right. So what we have to do is we use the right-hand rule. The right-hand rule said that if the magnetic field is along the direction of your fingers, in this direction, and velocity of the charged particle is along the thumb, then the force is coming upwards from your palm, right, for positive charges. So in this case, then magnetic field is going to the right, velocity is going down, so then the force is going downward. So the velocity is going into the page, so the force will be going downwards. Use your right hand and then just use that, like this is the direction of the magnetic field. This is into the page. The thumb is into the page, then the force will be pointing down, right, from your palm. So you know the direction. And for magnitude, you just substitute. Q is 3 times 10 to the minus 9 coulombs. And then V is 10 meters per second. B is 2 Tesla. Sine 90 is 1. So you get the answer. Force, magnitude of the magnetic force is 6 times 10 to the minus 9 newtons. Okay. Now, number 5 is 2 long current carrying wires. 2 long current carrying wires are 20 centimeters apart and placed parallel to the y-axis. Wire A has a current 2 amperes and the current is directed along positive y-axis. Wire B has a current of 3 amperes and it is directed in the negative y direction. Find the magnitude and direction of the net magnetic field at point P, which is midway between the 2 wires. So, you have 2 wires. Number 5, 2 wires. Current in wire A is going up. current in wire B is going down. They are 20 centimeters apart, and point B is midway between them. That means it's 10 centimeter from this wire A and 10 centimeters from wire B. Okay? In the test, the distance might be different. Okay? And the direction of the current might be changed, right? And people might get different different figures or different directions, right? So make sure you work your own problem. That's important. Otherwise, you will get wrong answer. Now, this is the finding the direction of magnetic field for a current carrying wire. So if the current is going up, you hold the wire like that with your thumb in the direction of the current. Then the direction of your fingers curling around will give you the direction of the magnetic field. So obviously for wire A, then it's going in because you will hold like this, right? But for wire B, you have to hold backwards because the current is going down, so you hold like that. So both ways, then your fingers are curling into the page. So magnetic field coming from wire A will be going in, and magnetic field coming from wire B will also be going in. That means they will add up. Okay? Now the formula for the magnetic field from a current carrying wire is B is equal to mu 0 I by 2 pi r, where mu 0 is 4 pi times 10 to the minus 7 Tesla meter per ampere. Okay? And this is what we call the permeability of free space. And r is the distance of that point that you are interested in from the wire. I is the current. So the net magnetic field at P, we now know that direction will be going into the page. And the formula is mu 0 by 2 pi IA by RA plus IB by RB. Then the distances are 10 centimeters, that means 0.1 meter, 0.1 meter. You substitute it, you get the result 10 to the power negative 5 Tesla. Okay, so it's very, very simple. All right, now let's go to the next problem. The next problem is about Snell's law. And in this one, the problem is a light ray hits the surface of a swimming pool at a distance 1 meter away from the edge and reaches the bottom as shown. So this little distance is 1 meter. This is water, and this is the swimming pool boundary. So this is the edge, right? This is the edge. This is the wall of the swimming pool. It is 4 meters high. And so it hits at this point and then goes down and hit the bottom at this point. And this distance is 1 meter. That's where the light ray hits the water. That is 1 meter away from the edge of the swimming pool. Now, in air, that is 1, that is the refractive index for air is 1. Refractive index for the water, I just give a number, it's 1.4. Usually people use like 1.33 and stuff, but 1.4 seems easy enough for you. And then we just have to find where it will hit the bottom, and then we need to find x. So I redraw the figure again. And then, first of all, I need to use Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. Once we know where it hits, then we know how to find this distance d, because this height is h, it is 4 meters. Once I know d, because I know the angle, I know the height, I can find d. Then, if I add 1 meters, I will get distance x. So that's our plan. So first of all, let me find the angle. So n1 sine theta 1 is equal to n2 sine theta 2. Let's call the medium 1 to be air. So n air sine theta incident is equal to n water sine theta refracted. Okay, I just call theta I and theta R instead of theta 1 and theta 2. Doesn't matter, you can just change the name if you want. Now n air is 1 as given. Theta I as shown in the figure is 50 degrees. So 50 degrees, and n water is 1.4, so sine theta R. So from there I can find theta R is equal to 33.16 degrees. Okay, so again, remember in the test, some people might get a different height like 5 meters, 10 meters, whatever, and then different angles, and then the refractive index might be different. So please make sure you do your own problem, otherwise you will get into trouble. Okay. Now tangent theta R is equal to d by h. How do I look at that? This is theta R, that's a refracted angle. D is the opposite, h is the height, so opposite divided by adjacent is tangent, right? So tangent theta R is equal to d by h. So d is equal to h times tangent theta R. So I find d is 2.61 meters. But d is only this little distance, right? The place where vertical distance from where the light ray hits and where the light ray reaches bottom, this distance is d, but what I want is x. And this distance is 1 meter, so then I have to add 1 to d, then I'll get x. So in our case, x is 1 plus 2.61, x is equal to 3.61 meters. All right, so that's number 6. Now the last problem, number 7, is a converging lens has focal length 0.1 meters and the object of height 0.02 meter is placed at a distance 0.5 meters away from the lens. Find the nature, real or virtual, and location of the image and magnification. Again, this is another simple problem. Let me show you. So, oh, by the way, I changed f to 0.2 instead of 0.1. All right, so I will change it in the paper. So the focal length is 0.2 instead of 0.1 like I read, okay? The height of the object is 0.2 meters and it is placed at a distance 0.5 meters away from the lens. So from here to here is 0.5. So from ray tracing diagram, you will see that the image will be formed between the C and F, right? Because your image is beyond C. Like I drew ray diagram for every possible situation in the lecture video, so you should review that. So the formula we have is 1 by F is equal to 1 by D0, that's the distance of object, plus 1 by Di, the distance of the image. And what we want is where it is located, so 1 by Di is equal to 1 by F minus 1 by Do, because Di is the image distance that we want. And 1 by F is 1 by 0.2 minus 1 by Do is given 0.5. So 1 by 0.2 is 5, 1 by 0.5 is 2. So the answer is Di is equal to 1 by 3 meters. All right. So then the image distance is 1 by 3 meters. So from here to here will be 1 by 3 meters. Okay. That's the image distance. Now the next thing is we need to find the magnification. and magnification is hi by ho. That is the height of the image by height of the object, and is equal to negative di by do. And negative di by do, I substitute it, I get negative 2 by 3. So magnification is negative 2 by 3. The meaning of negative sign is that the image is going to appear upside down. Okay, it's real image, and of course it will be upside down. All right, okay, and that's it.